Okay, so my name is Vlad Patryshev. The title was like on this announcement, somehow says I am Vlad contributor. Well, maybe I'll take this pseudonym later. So anyway, I'm Vlad Patryshev, and I'll talk about an implementation in JavaScript of a finger tree. I implemented it for my students when I was teaching them this year, when I started teaching them SICP in JavaScript. But this talk is more about like how our functional structure looks like, and let me switch the screen. So it's about finger trees in JavaScript. And this is me, and this is the link to this presentation, and it's not slides. It's a workbook in Observable HQ. So what is finger tree? It was invented like some time ago by Ralph, I believe, Hintze, and it's a very efficient data structure. A lot of operations take amortized constant time, and it's specifically efficient if the data stored or the key of the data belong to an ordered monoid. So what is a tree? Maybe some people know what a tree is, some not. So this is like a tree is represented by arborists. So a tree has a trunk, a tree has branches, like a branch has laterals, so like branches on branches. The connection between the trunk and the branch is called scaffold. And the top of the trunk is called leader. And if you have like some additional stuff growing, if you didn't trim it properly, you'll have water sprouts. And there are also suckers that you are supposed to trim away as soon as possible because they suck the water, the juice from the tree. So we are programmers, right? So programmers usually represent trees as if like the trees are in Australia and we are here in America. So top on the bottom and bottom on the top. So that's how we will look at it. In Haskell, a finger tree looks like this. So let's look at this data finger tree. It's either empty, so no data there, or a single value there, or it consists some digits of type A and a finger tree in the middle and digits on the left, digits on the right. And we wrap it all, we call it deep. So what's a digit? It's either one value, two values, three values, four values. And also because the inner finger tree contains nodes, so now we have not like plain data A, but nodes that contain either two values or three values. So look at how finger trees look like. Empty finger tree. A finger tree with just one value, so single. A finger tree with one value in the middle, four values in those digits on the left, it's 4A, and one value on the right. If we have like one more value added, so we suddenly have a node. So hit the node in the single, and it has two values. If we add more, so we'll have more nodes on the left, on the right, and eventually we can grow to something like this. On the top, we have like primitive values, then we have nodes of the first degree, then we have nodes of the second degree, nodes of the third degree, and they could be like either three. So it's like three trees. A node can have two or three subnodes or values. So here's how a tree grows if we add values. So see, we add values, but there are not more than four values on the right or on the left. And if there's more, we push them down there into the structure. So this is like, we removed it and then we are growing it again. So that's how it looks like if we are throwing in data on the right and taking them away on the left. And again, like, of course, you can add data on the left, add on the right, or you can split the tree. You can merge two trees. These are the estimates of operations on finger trees compared to other structures like 2-3 tree. It's all logarithm. Lists, vectors, hash tables, which is basically some operations just don't apply because what's a split for hash table? or split by measure, I'll talk to you a little bit later. But basically, we have either logarithmic or constant complexity. So we will improve if we don't have like anything, if we don't know anything about the values, we cannot be efficient enough. But if we have an ordered monoid, so ordered monoid is a monoid with like zero operation, with like merge operation, and with the comparison. So it's partial order, or maybe linear order. Linear order. Examples of ordered monoids are size of something like size of a tree, maybe, size of a value, priority, like value priority. So minus infinity, the neutral element for max, and we can compare strings with concatenation, or like price of the values inside. So if you stuff them properly there, will be really good, like, and operations will be pretty efficient. So let's look again at Haskell representation. So we have finger tree, which is empty or single, or like a deeper tree with digits on the left, like fingers on the left, fingers on the right, and a tree inside where values are already nodes. So I won't be using the standard JavaScript, like object-oriented, no. I'll be using the kind of JavaScript that you can find in SICP book. So here's a prototype that just represents the data. So it's a structure that has like empty, which contains no values, single, which contains a value, tree, which contains like here, left, right, and a finger tree in the middle. So it's a subtree. And now, what are the values? Digit 1 is just contains one value. Digit 2 contains two values. Digit 4 contains four values, and node 2 takes two values, and node 3 takes three values. And what does it mean? It means that we'll have to stuff in some operations here, because otherwise, okay, so it swallowed the value and it doesn't do anything here. But it's a function, and at least we can build something. So what we built first is serialization. So let's introduce methods of those different sorts of trees, different kinds of trees. So empty, to string of empty will return just these angle brackets. Single will return, it will say single and the value of that A. Dollar by dollar, yeah, whatever. So, oh yeah. This is formatting. So this is observable HQ, like string interpolation. So backtick means that, well, we'll stop the value there. So tree, because a tree has left branch, right branch, and a subtree. So to string will do what? It will say tree, left branch, subtree, right branch. Digits are like, I'll put them in square brackets. So one value, two values, three values, four values. So now we do something with the value that we provide, right? And nodes, a node can contain either two values or three values. So we say node and then the values. And those values, they will be stringified. So the string will be producing stuff like this. So let's look at an application, right? So because we created finger tree here, so this is the object that produces this data type, data structure. So let's build a tree that contains like digit 2, two values here, 11, 12, then a single in the middle, and one digit on the right. So its string representation would be, well, because it has two strings, right? Its string representation would be 3, and then this 11, 12 in brackets, and single, and 13 brackets. So you can see that it's something like this, or something like this. This kind of structure. If we throw in more data, like ABC and DE and LGH, so we'll have this kind of structure, ABC on the left, and on the right, the last one. And in the middle, we have a tree. And this tree contains a branch containing node, DE, and another on the right, it contains node, it contains a branch with two figures, node IG and node KLM. And in the middle, we have a single with node inside. So that's how it works. And we can make it like more and more, we can go deeper and deeper in the structure. So, but again, this is the way we can build the data, but maybe we throw in more operations. We like said that, cons is efficient. So let's implement cons. So here I pulled out the implementations from that structure that I returned, right? So all these empty single digit one and so on, they're defined here. And because it's, well, because it's JavaScript and because it's kind of primitive version of JavaScript, so I have to declare those values, but then I define them. Like single to string is the same, but cons, so we have a single, right? If we add a value to single, we'll have this tree, B on the left, the one that we add, and digit one on the right. So let me show you the picture. This is single, and we add a value. So that value will be on the left, and this value goes on the right. And the same, like, how do we add a value to an empty? Well, basically, we just call single. How do we add a value to a tree from the left? So we do cons to A. We do cons to the left branch. And the left branch also needs subtree if it wants to throw in some value inside. And digit one, we do cons, so we add a B. Digit one already had an A. So what it does, given a subtree and a right, well, because it needs them to like return a tree. So we create a branch with two values on the left, the same subtree and the same right. So the same digit two, we just add one more value, C, to this AB. So we have digit three here. Digit three, we add one more value, D, A, B, C, and then we produce a D on top. So digit four is trickier because we have four, we cannot have five. So we pass an E, and what happens here? We already had A, B, C, D, right? So E is left with this A, the leftmost element of the previous tree, but the rest goes down into subtree. So we create a node of three values, B, C, D, that we had in this branch, and we push it down into subtree. And subtree does the same cons, so we don't know what it does. It's a tree, right? So it does something, it will probably do the same thing, like take its left and try to push. So, and what about node? We don't push anything to node, we just build node. So it doesn't, nodes don't have the cons method. So how does it work? Like here are two examples. I wrote a method called build, which takes like if build a tree of n values. So if it's zero, it's just an empty. Otherwise, we do by recursion build from n minus one and do cons with n. And so let's run it. Yeah, so this is how it does, how it works. I use promise to delay, so it's adding like 4. And it produces the same tree. Oh, see how it is. It goes down. Then we're appending 7, appending 8, and then again push, and then again, and then again, and then again. Ah, so 11. We're done here. So cons, okay, the like symmetrical like mirror like operation to cons is snok. Just append on the right. So in this piece of code, I wrote snok, but I didn't add cons because, like in this example, we just didn't need it. So if we have a tree, how do we append an A on the right? We append that A to the right one, and we pass left and subtree to that right to produce a tree. So if we have a single, a snok would be just creating like a single already has a B, a value B. No, it has a value A. So if we push B, we'll have a tree where A is on the left and B is on the right. So digit 1, we just push the value. Digit 2, we push one more value. So we had A, B, we add C. Digit 3, we had A, B, C, we add D. But digit 4, we push E, but we push it on the right. So we'll keep D on the right branch and create a node with A, B, C and push it to sub3. Left sub3 is left intact. So this is what we will have, like empty. Then snug 1 will be single 1. Snug 2 will be tree consisting of 1 on the left, 2 on the right. Then we push 3, push 4, push 5. And if we push 6, 5 and 6 are left, but node of 2, 3, 4 is inside that single. Okay, so we grow, we have 8. Now we push 9. We create a node of 5, 6, 7 and push it inside that single. And that single, you know how it grows. It creates a tree with 2 nodes and empty in the middle. So that's how it grows gradually to like snug of 7. This is not exactly like very beautiful, but I'll get a beautiful representation a little bit later. So because this structure is symmetric, we don't have to write like fold left, fold right. Well, I mean, we can, but it will be basically, it will be looking the same. So here, how do we do fold on a tree? We just scan the whole thing and go deeper and do the fold inside. So what does fold require? It's a monadic operation, and we need a binary operation, and we need a neutral element, Z. So this, I defined it for like working with this, with the values that don't belong to the tree. So we have that value, and if that value has fold left, so we apply that fold left with this operation and neutral element. Otherwise, we just do this operation on neutral element and the value. So for instance, we add numbers or whatever. How do we do that for a tree? A tree consists of left branch, right branch, and the middle tree. So we fold the left branch. No, let's define a folder, the thing that does operation, that fold operation. And then we do left sum, the sum of left branch, right sum, the sum of right branch, and the middle sum. And we blend them all together, left, middle, right. And we assume that the monoid is associative. So we know that, like, we have to do it in this order, but we could group it differently. So single, what do we do with single? Foldle, it just, what? It contains a value A. So it could as well return A, but for simplicity, we rather do this foldle. And why? Because if the value is a primitive value, then it's A. But what if it's a node? We have to do stuff in the node. So digits, it's obvious that if we have like a 3 digits with 3 values, so we fold for each value and do the operation, like blend them all together. So what do we do with the node? We have A and B. So we fold the values inside and then apply this operation. So that's eventually how we do A. And we produce this. Here's an example. Here's an example. We build a tree like this. So given an N, we build a tree that consists, that has A, B, C, and all these values stored there. Okay, so we have a tree that looks like this: A, B, C, D, and then deeper E, F, G, and then deeper H, I, G, J, and so on. How do we, like, here's an example of summing up. We sum them up like this: an empty string as a neutral element and just a concatenation with space between 4 values. So we do that. Well, we do sum, right? So we fold left. And we'll have this A space B space C. And why do I do trim? Because on many occasions we'll have like a space somewhere on the right, empty string. So empty string with space, it's an empty string. I'd rather trim them. So that's how we have this thing. If you add instead like, and run it. Yeah, that's it. pulled around. So to improve performance, we need something. We need to know like the sizes of nodes. So here, let's introduce this size. And suppose each value has a size. So if the value inside is primitive, so it just, its value is 1. Otherwise, it's the size of the node. A node contains like 2 or 3 subnodes. Those subnodes contain more. So we just add the sizes. So we cache the size. Like given a tree, its size is the size of the left branch, the size of right branch, and the size of subtree. So if I have like digit 1, the size of A, otherwise it's the sum of sizes and so on. And for nodes, the same, like we add the sizes. So suppose we build these strings, this tree again, just in the opposite order, like Z, Y, X, and so on. There's A in the beginning. Oh yeah, here, A. So if we check the size is returned because when we build this tree, the tree has this size. So once we create it, the size is already cached. So we don't recount it again. So it's 26. And then if we have a size, we can search by index. So let's introduce a method called at. So like given a value, like let's do at something like at the digit, right? So we do at on that value. So at like takes an index. Given a value, it takes an index and tries to find the value that is if the index is below 0 or bigger than the size of A, so it's not there. If we are dealing with a part of a tree, then we apply that method at, so that indexing in extraction by the index. Otherwise, it's exactly the value. No, if I is 0. So we'll find the value at a given index. Again, how do we do it like for a tree? We try to find it on the left. If not, then try to find it in the middle, and then we find it on the right. And because it's logarithmic, so basically all search is logarithmic. Because the tree is exponential, like what do we do with the node? We try to find it in the left subnode or in the right subnode. Here's an example, like I create a tree consisting of A, B, C, D, and so on, like this, right? And then I find elements sample at 0 and then sample at 1 and so on. And I push them into out string. So that's what we find like at 0, at 1 and so on. And then I do the same in the opposite order. So number 25, number 24, number 23, and so on, number 0. So that's how this find works. Well, because that's this index, right? But we don't have to work with just indexes. We can, instead, we can introduce a measure. Here, I create a tree that takes a measure function. And what's a measure function? It's a function that basically calculates a measure of a value. So it applies to a value and it returns something about that value. Maybe like the length of a string, if you store strings, not characters inside the tree. Otherwise, we call measure method of the thing. Like in a tree, the measure of a tree is the sum of measures, the measures of left, the measure of middle, and the measure of right, and so on. So it's the same as length, except that we call measure method. So here's an example when we use measure as length. So we create a finger tree with measure that is just the length. And so we do the same, like index find by measure is find by index. But in this example, I create a tree consisting of this phrase from the Raven. Once upon a midnight dreary. So I created this just to show like this is the index of each character. But what we store in the tree is words. So how do we find the word? that is somewhere like at a given position. Position 10 points to midnight. That's a character number 10 in the string. Position 41 is the word end. So that's how we find it here. I created, this is just a show, right? But I call sample at 10. And because the measure is the position, so the string at 10 is the word, the value at 10 is the word midnight. It's not like letter I, because we stuff once upon the midnight dreary. So that's what we do, right? Like we create this thing by recursion. Okay, so these are examples of operations that we could do. But then actually I figured, well, that's not the right representation. When we create a node, right? So we don't like, we don't need references. We have a node inside the node inside the node. So it's like if you cut a trunk, if you cut a branch, you'll see those like sub branches that grew there before. So that's the idea behind a better graphic representation of finger trees. Let me see. Let me get there. Here, let me start the show. We are adding things, so see, we take the tree and we pull them into the next level. So these are the nodes. And I surround them because like that's what we get together and push into another node. So that's how the things grow. And you see it's more compact and it represents the idea of the tree growth here. So we're adding, rather than this is like carry, it's like carry in, I don't know, in positional system of, yeah, I'm accelerating it because like there are too many letters in this world. Yeah. Okay, so we're done with Romanian letter T, I believe. Romanians can correct me. So that's how it is actually, like the top level, primitive values, second level, second order nodes, third level, third order nodes, a node inside the node and primitive values inside, and so on. And because we were appending on the right, the things are bigger on the right than on the left. But it doesn't make it more complicated in the search. So that's how it is. And also, you can see that all nodes are of level 3. There's nothing that is of level 2. There's a reason for that. Actually, 2 or 3 alternating is good, but here, when we only appended on the right, when we were doing SNOC, so that's all we could produce. So here's another example when we append left and right. So it's more symmetrical, right? That's how it grows. I'm not showing you the source code of this because it has like too much code dedicated to graphics. So it's VG. So this is how a tree looks like if we append alternating from on the left and on the right. And I believe we also added more values. No Armenian letters. Yeah, so that's what we have. That's how it grew. Okay, but I said that there are like efficient operations, split and merge. I wouldn't show you split, but I'll show you how merge works, like given two trees, how the stuff works. So here are two trees and they're going to merge. Okay, so how do we merge? We start at the top, pull away these branches and try to group them. We have 7 values, okay, 2 and then 2. That's where nodes of size 2 are coming into the game. Okay, so next level, tier of these things, and we have at most like what, 11 nodes. So we group them again and we push them down. Okay, done. But now there's nothing on the right. So let's attach those nodes to the longer tree and then merge the trunks. Done. We have 2 trees merged. And you probably saw that it's logarithmic, right? So that's what it is. And I'm done. And here are the references. Here's also the link to this presentation. It's also on the top. And the presentation is observable HQ /@vpatryshev/finger trees in JS. So thank you. And also thanks to Lexi and Oli and Salar and all other organizers. I don't think I'm, KP. And special thanks to Mike Bostock. Oh, it should be C, right? Yeah, I'll fix it. For like producing this beautiful engine, beautiful workbook engine where like we can use it. So thank you. Any questions?